So, in this lecture we will do some numerical problems to understand the CD nozzles further. So, whatever concept we have been discussing in the last few classes, we will try to see it from a numerical point of view. Okay. So, keep your gas tables near you. So, the first question I have here is, so I have a converging diverging nozzle. The throat area is 10 millimeters. The exit area is 30 millimeters. The stagnation pressure is 10 atmospheres and T0 is 300 Kelvin. Okay. Nozzle is operating at design condition. Find m dot, find V star at the exit, C P exit and M exit. Length of the nozzle. So, I will read the question. So, I have a nozzle here whose throat area and exit dia is given. Throat area is so its throat area. So, this is millimeter square. So, 10 millimeter square and 30 millimeter square. So, nozzle is operating at the design condition for this particular stagnation pressure and temperature. Find the m dot, V star at the exit, and P exit, pressure at the static pressure at the exit, Mach number at the exit, and sketch how the pressure variation along the length of the nozzle. Okay. So, first information is operating at design condition. Okay. So, when you read this, the first thing that comes to your mind is flow is isentropic and your M exit is supersonic. Flow is chalked, implies the m dot at your throat is your m dot max. So, these three information should come along with this particular statement, which is the design condition. So, if your flow is chalked, then it means my AE by A thought is same as AE by A star. Okay. So, if I take that information, is nothing but 30 by 10, that is 3. So, for this AE by A star, so AE by A star and Mach number, I have two solutions. Now, I also know that my exit Mach number is 1. So, my M exit associated with this particular ratio is either the subsonic solution or the supersonic solution. So, I take this table, look for gamma equals 1.4, A by A star is 3. So, I look for A by A star is 3, which is going to be around 0.2. Or .64. Okay. Since we already know this is a design condition, my M exit is 2.64 and not the subsonic one. So, if my M exit is known, I can substitute my mass flux A into P0 by root T0 root of gamma by R into M into 1 plus gamma minus 1 by 2 M square minus gamma plus 1 divided by 2 into gamma minus 1. Okay. So, my area at the exit is 30 into 10 power minus 3 the whole square. P0 is 10 at most, 10 into 10 power 5 divided by root of 300 Kelvin into root of 1.4 divided by 287 into M exit is something which we already know now, 2.64 into 1 plus gamma minus 1 by 2, 2.64 square to the power minus 1 by gamma by 2 gamma minus 1. So, that would be your M dot. So, once you have your M exit, this is my M dot in kg per second. So, once I have my M exit, I can get P by P0 or P exit by P0, which I have to look at the gas tables to find 2.64. For 2.64, my P by P0 is 0.07, P by P0 is 0.0471, from which I can get P exit as 10 into 0.0471, which is 0.471 atmos. Likewise, I can also get my T exit by T0 or rho exit by rho 0 if I know the values of rho 0. Rho 0 I can get it from PV equals RT, PV equals RT, and then I can get the exit density of the fluid, exit temperature of the fluid. Now, since gamma is known, I also know this value, which is the constant from which I can get P naught by P star or rho naught by rho star. So, if I know these values, I know already m dot. So, from m dot I can write rho star into A star into V star at the exit at the throat equals my rho AV. So, the throat area I know, throat area is 10 millimeter square, which is 10 minus 3 to the power square. Rho star I would get from here, okay, which is again a constant. From m dot I already have computed. What is this value? 0.023. So, I substitute that value here, that is my m dot. Rho star from this relation for a gamma 1.4, from which I can get my V star, which is my V at the throat. This is so the question here is V at the throat, V star at the throat. So, since it is already Chow condition, the V here would be your V star, because m equals 1 at the throat. So, your V at the throat is your V star, okay, from which you can get V star. So, we have computed m dot, V star, P exit and m exit. Now, sketch your pressure variation. Okay. So, I have my nozzle here, P0 is 10 atmos. I do not know my PB, but I know my A throat is now my A star and Mach number here is 1. So, P0 is 10 atmos. This might have reduced to some value and it had now taken the isentropic route to get m exit to be equal to 2.64. So, this solution m equals 0.2 we have not taken because it is already known that it is working at the design condition. So, this is my design condition. So, my P exit is PB. Okay. So, even though we do not know, we do not have that information about PB, but the back pressure, the information that the nozzle is working in the design condition means my exit pressure is same as my back pressure. Okay. So, which is all equal to what? which is equal to 0.471 atmos. So, likewise you can draw the Mach number variation also. So, you can so at somewhere along the throat my Mach number is 1 and then it reaches 2.64 at the exit. Here it is 1. This is my Mach number variation. Okay, fine. So, the same nozzle, throat area is same, exit area is same, except that the stagnation pressure is now increased to 15 atmosphere and it is working in the design condition. So, it means that there is no change in here. So, this is area ratio is same, Mach number, the exit Mach number is same, we have not taken the subsonic solution, everything is decided by the area ratio as we have already discussed before. Everything here is decided by this particular area ratio and this Mach number is fixed, design Mach number is fixed. Now, when it comes to the mass flow rate, that would be different because now P0 is different. Okay. So, this value would be something else, which means my P exit ratio is same, P0 is different. So, my P exit is also different. So, instead of 10 it is now 15. Yeah. 15 into 0.047, 0.766, 06. Okay. So, my P exit is different, my m dot is different, P exit is different, again it is in the same design condition except that P0 has changed, and here again the T0 is same. So, this ratio would be same. So, accordingly your P star would change since the P0 has now a different value. So, your rho star would also be a different value. So, here again your m dot is different. So, your V star would also be different. Okay. And here same plot except that this value is now 15 atmos. The pressure is, back pressure would be something else which is 0.706, exit Mach number has remained the same, there is no change there, and the Mach number plot is the same, the stagnation value. So, it is just stretched a bit. Okay. So, the throat Mach number is still m equals 1, the pressure ratio is adjusted such a way that the exit condition is same. Okay. So, as I discussed before, this is a steady state solution. When I say the stagnation pressure has been increased to 15 atmospheres, it is a different case, it is a different study. So, the stagnation reservoir pressure that is supplying air to the nozzle is now 15 atmospheres, that is all. Okay. It is a steady state solution, remember that it is a steady state solution, there is no unsteady part that has been discussed here. Okay. Okay. Now, we will go to the next question. So, the next question is, let us go back to the first question where my P0 is 10 atmos. Okay. Now, I change my A throat to 5 millimeter square. Again it is in the design condition, find m dot V star, P exit, m exit and sketch the pressure variation. So, the nozzle is now different. Okay, the pressure is same, the stagnation pressure is same, stagnation temperature is the same as before, 10 atmosphere and 300 Kelvin, except that the throat area is now reduced to 5 millimeter square. Now, since it is at the design condition, all these inferences that we made earlier is true. Flow is isentropic, m exit is greater than 1, flow is choked. So, m dot at the throat is the maximum m dot that you can get through the nozzle. AE by A throat is same as my AE by A star, but now the A star value is different. From 5 from 10 it is now reduced to 5. So, this is 30 by 5. So, the value is 6. So, accordingly the Mach number at the exit is now different. If you look at the gas tables, AE by A star, a value of 6, around 6 is 0.095. And around 3.35. Okay. So, actually you have to interpolate between 3.35 and 3.40. Okay, but let us take for the explanation purpose, let us take 3.35, and since this is at design condition, we would take the supersonic value, which is 3.35. Okay. So, your area ratio is now different, m exit is different. So, the moment you have changed the area ratio, you have changed the design Mach number at the exit. Accordingly, everything else will change. Okay. So, even though your P0 and T0 is same, now the exit Mach number is different. So, everything has changed. Okay. And you can continue doing whatever we had done for the earlier problem likewise. Okay. Okay. So, now we will move on to the next question. Nozzle A exit by A throat is given as 1.53, P0 is 1 bar, find m exit for E exit to be 0.94 bar, 0.88 bar, C 0.75 bar, and D 0.145 bar. So, I have the nozzle with this particular area ratio, I have a reservoir pressure of 1 bar. Now, if the P exit is changed to these values, what is my Mach number? So, if it is a design condition, we do not know whether it is a design condition or not, but let us take if the nozzle is at design condition, AE by A throat is your AE by A star, which is 1.53, okay, which means your Mach number at the throat is 1. So, if AE my A star is 1.353 and this is my if the nozzle is at design condition, the throat Mach number is 1. If that is the case, then my P by P0 associated with this particular Mach number is P by P0 associated with Mach number 1 for gamma equals 1.4 is 0.528, okay. So, if the pressure ratio is such that this particular pressure ratio is reached, you would see a design condition, okay. So, if I plot the pressure values, P0 1 atmosphere goes to some value and then it takes to a supersonic which is your design condition. Okay. But this can also take other isentropic solution, which is my m less than 1, this is m greater than 1, here m equals 1, and if I change my PB in between, if the PB is such that my P exit equals PB is somewhere between these two, we have also called this as P critical 3 and this is P critical 1. So, if the pressure is between these two values, I am going to get a subsonic Mach numbers, isentropic solution of subsonic Mach numbers. So, the question here is the P exit is progressively decreasing, okay. So, I have a case 1 here, maybe here, maybe here, maybe here, okay. So, I need to find what exactly is that and accordingly find my Mach number, okay. So, that is all I need to do here, but identifying this curve is the important part in solving this problem. So, all I need to check is if the pressure ratio is above or below or this condition. So, this would be my so called P star by P0, okay. So, my P E by this is 1.53, okay. So, the m exit will have two values, m exit will have two values, subsonic value and supersonic value. So, AE by A star 1.53, 1.53, gamma equals 1.4, .53 is m equals 0.42 or 1.53. So, I look at this table, m equals 1.53, m equals 1.88, okay, which means this as m equals 0.42, these are isentropic solutions, this is my 1.88. Okay. So, this area ratio decides these two pressure, these two Mach numbers. Okay. So, that is decided by this. Okay. Now, m equals 4 my P by P0 at m equals 0.42 is, I look at the tables, m equals 0.42, I would get P by P0 as 0.886 or m P by P0 at m equals 1.88, m equals 1.88, P by P0 is 0.154. Okay, what does this mean? So, get if my PB, which is also my PB by P0, which is also my PB by P0. If my PB by P0 is this pressure, I am going to get this Mach number, which is 1.88. So, if my PB is equal to P0 into 0.154, I am going to get this Mach number, or if my PB is P0 into 0.886, I am going to get the subsonic Mach number. Both are isentropic solutions. Okay. So, any pressures in between will give me a subsonic between this value and the critical pressure 1 will give me a subsonic solution. Okay. So, all I need to check is whether these pressures are above this pressure ratio or below this particular pressure ratio. Okay. So, let us check the first value. A is P exit equals 0.94. Okay. So, my PE by P0 is 0.94 divided by 1, which is 0.94, which is greater than this, which means it is going to lie here in this region, some curve here is going to be your case A. Okay. And the Mach number associated with this P exit by PE 0.94. So, I take the tables, look for 0.94, 0.94, 0.94 is 0.3. So, my exit Mach number for this particular back pressure, which is also my PB by P0. Okay. So, in this region my PB is also equal to my P exit, which is 0.94. For that particular pressure ratio, I would get my exit Mach number to be 0.3. Okay. Now, I take the next pressure. B, P exit is 0.88 bar, or my P exit by P0 is 0.88 bar, which is close to our isentropic solution of the subsonic case, which is our P is P critical 1. Okay. Will give me exit Mach number of 0.42, which we have already found. Okay. So, if my exit Mach number, to get an exit Mach number of 0.42, which is an isentropic solution of the nozzle which we are given, the pressure ratio should be 0.88, which we have already seen. Okay. Now, take the third case, which is 0.75 bar. Again do the same process 7 5. So, I look at the tables. Seven five is m equals 0.65, okay. And the problem here is this pressure ratio is between these two values, hence we know that this is a non-isentropic solution. So, we cannot use this relation to get the Mach number, because okay, this is the isentropic solution, but P by P0 is between PR1 by P0 and P critical 3 by P0, which is non-isentropic solution. Okay. How can you prove this? You can for this particular pressure ratio, for this particular Mach number, you look for your area ratio, show that your throat area is larger than your star value A star. So, A star is larger than your throat area. So, hence this cannot be a possible solution. Okay. So, this pressure ratio, easier thing is we have just demonstrated that that particular pressure ratio is between PCR1 and PCR3, which is a non-isentropic solution. Hence, your pressure ratio will not give you this Mach number. So, this Mach number evaluated from your isentropic solution is wrong. Okay. So, this cannot happen. We do not know what is the Mach number there. We will have to do after studying shocks, we will have to evaluate what is the Mach number there. We will do that particular case later. Okay. Now, let us look at the fourth case. Fourth case, the pressure ratio is 0.154, which is what we had seen to be our isentropic solution here. So, your Mach number at the exit is going to be 1.88. So, that is a case that is drawn here. So, this is my A, this is my B, and there is some other solution here which is my C, and this is my D. Okay. So, all these points A, B, C and D shown in this graph A, B, C and D.